Hello, everybody. Let's get started. So first of all, welcome to the first computational social science seminar of the year. And it's a delight to have a distinguished speaker for the first seminar of the year, Dr. Yeol, commonly referred to as YY, is an associate professor at Indiana University School of Informatics, Computing, and Engineering. His research focuses on developing network science and machine learning methods and applying them to complex social and biological systems. He was trained as a physicist from the Korea Advanced Institute for Science and Technology and was at the forefront of significant research movements in what has come to be known as computational social science. I have a couple of examples here. So the first one is his article published in the early 2000s on comparing the structures of the online social networks of the Psy world in Korea, Orkut, and MySpace. Was one of the first papers to crawl massive amounts of digital social data from more than one platform and submit those data to rigorous network scientific scrutiny. Creativity and deep intuition about networks have contributed to viewing the basic and entrenched concepts in social science. For example, in his postdoc years at the Center for Complex Network Research with Albert Laszlo Barabasi, YY introduced innovative ideas for thinking about social groups consisting of links between nodes rather than the nodes themselves. Another example, his more recent work using LinkedIn data offers a different way of thinking about clusters of economic activity that we usually call industry. In contrast to the top-down classification of economic production that is used in classifying industries, the approach that YY and colleagues present is a bottom-up approach of thinking about economic production in terms of the job mobility patterns of millions of people. The list of innovative ideas and papers goes on and on. So it's a great pleasure to have the opportunity to listen to YY's most recent work. So without further ado, I turn the floor to Professor Yong.
Thank you so much for having me, and thank you very much for kind introduction. You're really digging to my comment.
Big fan.
Please appreciate it very much. Yeah, so today I'll talk about graph embedding with somewhat clickbaity title. Yeah, so let's start. So you have probably seen this painting. Yeah, so one thing special about this painting is that it won State Fair art competition from Colorado, I think. Another interesting fact about this painting is that it was drawn by Midjourney. So the artist crafted the prompt, and the actual artwork was done by AI system. And you have seen all this like amazing artwork. I really like it. Teflon Jupiter Gate. You can see everyone in the face. Yeah, you have seen it, right? And the thing is, like, we don't really fully understand like what's going on like in the machine, right? It's really hard to comprehend what makes this like amazing capacity. Like for instance, in the case of large language models, this paper showed that you can just say, let's think things step by step the language model, and then you can kind of induce like more of a chain of thought reasoning from the language models. And there are also like a lot of graph embedding, graph neural network application that shows a lot of promises across like so many domains. And of course we have ChatGPT and so on. But as a recovering physicist, it's kind of troubling that we don't really understand like the mechanisms, and they remain largely as a black box. So this talk is a kind of an effort to open up that black box a little bit, at least for like simpler models. And I'd like to thank our group's postdoc, Sadamori Kojaku, and he has done a lot of contribution across all the work I'll present. So I'll start with the power of representation learning. So the thing is, like in computational social science, we deal with so many different types of data, complex data sets. Text is one example, but we have networks, images, videos, and so many different data sets. And that's really challenging because usually in traditional social science, you work with like surveys and much more structured data. But now it's unstructured, and it's really difficult to deal with them. But fortunately, machine learning and all these like computational techniques come along, and they allow us to do something about them. Like for instance, the traditional pipeline is like you have data, you extract some features, and then plug that into the model. You have a giant regression table and so on. But I think what people gradually realize more and more and appreciate is how important the representation is. If you can get like really good representation, that whatever model you use may not matter too much. The representation hold the power. And I think that was, I think, one of the important reasons, lessons from deep learning. Like, machine learning is all about getting good representation. Once you have good representation, your model matter less. Right? And then other really important lessons I'll say is that you can let the machine learn all this representation, and that tends to work really well. And I just like rather than like humans crafting features based on their assumptions and preconception about how things work. So prototypical machine learning models, I'll say, goes into computation can be represented something like this. So you have a very complex data set, and then you have some encoder that represent that into some vector representation, some numbers. It can be applied to like more traditional machine learning, others apply to like neural networks. And then you have also decoder. It can transform this kind of dense representation back into this complex data form again. A lot of AI generative art are focused on decoder, but also they need encoder to understand this complex data. And this kind of bottleneck is usually called embedding, and that's the representation that holds all kind of power. And an interesting thing is they live in a vector space, right? And it's a space. And that means we can kind of try to interpret them as an actual space. And I think that's a really interesting kind of idea that emerged out of the learning and so on. Like for instance, if you use like a lot of to embed words, get the word, the vector representation of words, and then you can plot literally as a space by projecting them onto like white to black, rich to poor, their location in that space matches pretty well with what you get from social surveys, how people think about those words and genres, music, and so on. If you train word-to-vector model on the abstract of material science papers, then the space that these words, terms representing the materials, they form certain geometry that reflect the physical properties of those materials. Or you can find the hidden latent space where the faces live. And then you can find kind of the directions where you can add more hair or subtract more hair, add glasses, and so on. So there are like meaningful accesses you can find in these embedding spaces. Another example, houses from like Victorian style to modern. And what I want to kind of argue is that the ability to think about this embedding representation space of complex data sets allow us to kind of imagine better. What I'm saying is we are now have a space of words. If you without thinking about embedding space, words are words, and it's hard to conceptualize in our head how they are related. But once you think about this embedding space, now we are thinking about the space of words, actual space. And we can think about space of materials, space of faces, and so on. And that allows us to think about or ask questions, interesting questions. Things like, oh, how does words move in the space over time? That's like really natural way to ask an interesting question about the kind of temporality of this meaning of the words. Like, for instance, here it shows that the word gay moved from left flaunting, sweet shuffle, kind of that vicinity to the current meaning. It changed a lot. Like, and you can see it in that space. Another project we are doing in the science of science space is like, can we model trajectories, like how scientists move in the space of knowledge as something like the murmuration of birds? Like, can we just model each scientist as a point in the vector space of the knowledge space? And then can we study how they move in the space to understand general laws and patterns of this endeavor of scientific enterprise? And I think one of the kind of base model that opened up this idea is our Quebec. And it was kind of striking to see how well it captured this analogical relationship between words. The famous one is king, queen. Like queen is similar to king minus man plus woman, the vector space. So it's like really cool. And it built on the idea of like the question of like how to encode the meaning of a word computationally. And if you think about it, it's not easy. If you just represent hello world in just ASCII format, it doesn't contain any meaning about those words. Okay? And word to back is based on the idea that the context is what gives you the meaning of the word. So this example, quick brown something, jumps, blah blah, and he is cunning as thing. And you can immediately picture this is about fox, because it should be able to jump. It's cunning and it's quick, brown, and like chicken. So it must be something that has the quality of fox. And the context can be thought as a kind of a document, for instance. And once you have a document and term metrics, you can factorize. And there are many methods, but easiest way to think about it is NNF, non-negative matrix factorization. And basically you transform document to term relationship into document to topic, and then topic to term relationship. And by having that, you reconstruct that whole data. Yeah. So, yeah. And this one element will tell us about like a document to term similarity. And that's the product of these two vectors, document to topic, how this document has all these topics, and then how this term is related to a bunch of topics. And if you know that, you can figure out how similar they are. And then we can go more fine grained into the idea of language model, which is just asking what is the probability of this sentence. So it's a joint probability of all the words you are seeing. And that can be transformed into a bunch of conditional probabilities. Once you know conditional probabilities, you can basically model our language. And it boils down to the question of what's the probability of the next word. And we have context words and then target words. And once you can answer this question, we have a pretty good model of the language. In fact, all these BERT and GPTs are essentially that. It's trained on that task. Essentially, what's the next token? That's like GPT, right? It's incredible that this simple task can teach the model how much about the language and like human culture. It's mind-blowing. And then the idea of the neural language model is let's just use the neural network in that process instead of like doing metric spectration. And word2vec is really a simple model. You are not even considering full context that appear before or around. You are just considering one word, one term, and skip the others. And that's why it's called skipgram. And you're just answering this probability question. Given a context word, what's the probability of the target word? And if you can answer that, we have some language model. Yeah, and then we can calculate, we can aggregate all these things into this one term. And then, yeah, so that's basically the likelihood function of the word2vec model. Yeah, but we haven't touched how to actually estimate that conditional probability. And that's where the actual word2vec model innovation comes in, which is, let's assume that we have really good pair of word embeddings. Then maybe we can think about two vectors each word has, like key and queries. This is a transformer term, but I'm using it because I think it makes sense here. So each word has a query and key vectors, and the conditional probability that given the context word, the probability to see this target word is just a function of these two vectors, of the query of the context word and the target vector of the key vector of the target word. Okay, and then a simple choice is a softmax function, and yeah, that's the word2vec model. And you can think of it as again a metric spectration. And there were paper showing that. And essentially we have a word-to-word similarity matrix, but we are not constructing that matrix explicitly, but we are constructing the factorized low rank matrices by thinking about word vectors. And we have two vectors on that side, on that side. And then we don't calculate that. And let's use neural network to estimate on the right side directly from the data. Yeah, so that's the word. Yes.
Can I ask a clarification or maybe a confusion question?
Sure.
What do you mean by query and key? Do those somehow correspond to these dimensions, or is there some intuition you can provide for that?
Yeah, so I think the intuition is like think about database, right? So I'm the context word, and I'm trying to figure out which word will appear in the target location. And I'm sending a query and see which vector matches my query. And everyone has a receiving words have a key vectors. And if their key vector matches my query vector, then I'm predicting that, oh, this word may appear right in that context. So I think that's the intuition.
I see. So is the idea that I might have, I mean, I'm trying to understand why they aren't the same vector space.
So there are like some studies that are showing that if you have enough dimensions, enough large dimensions, the key query vector converges into the same vector, essentially. So,
You train differently for a key vector versus a query vector somehow?
it's in the likelihood function. So you calculate the dot product of query vector of the context word and then key vector of the target word. That's in the likelihood function. So they are kind of jointly trained.
So if it's symmetric, why aren't they just the same? Or I guess you said they do converge to the same.
Yeah, so you can think about like query vector as something, okay, if I see this word, what kind of word do you expect? And key vector is something like, well, I guess it's very similar, but it's like, if I'm in context, what do I expect? Versus like, which context do I expect as a key vector? That the target vector. So it's like two different directions to find the word. Yeah.
Thanks.
Yeah. It has slightly different meaning, but in many of the calculation we consider that as the same vector. And it's not far from yeah, very good question. And please ask questions, interrupt me. I think it makes more useful. Yeah. Yeah, so that's word spec. But I think interesting thing is like there's nothing special about like human language or words. You can plug in any entities in the space in the place of the words. So one example, you can put images and train that with the word at the same time. So here, an example of like, okay, here's like this clothing. I want to have a kind of version that I can wear during my pregnancy. You add the vector for that clothing, you add vector for pregnant, this word vector, and then you get the vector similar to those clothing. Yeah. So you can do this kind of crazy. And also, you can apply to graph data. The idea is thinking about like graph model instead of language model in the same way that a sentence in a graph context is a sequence of nodes in a graph as somehow generated. And then we are obtaining vector representation of every word in the sequence by just plugging that into word-to-vec model. The most natural way to generate sentences is just random walk. So if you generate many random walks, if you are closer in the graph, they will appear more likely together and they will have a similar embedding. And that's how graph embedding basically works. Yeah. And again, you can think about it as a metric factorization. That's not. So exhibit number 1 for unreasonable effectiveness cycle. This work is done by Peng here with the help of colleagues here. And we call like periodical feedback, which is very simple idea of like instead of using words and sentences, we are using citation network and papers and journals. So we create this network of citations, follow the edge, create many random walks. And we use the journal as the word to get the sentence of journals. And then that gives us the embedding of journals. There's journals and conferences. So each node here is a conference or journal. And the color is kind of classification system, manual classification system. So yeah, so that's the kind of the space of knowledge in a sense. The map is very interesting because if you zoom into some areas, you see interesting stuff. For instance, in the middle of social science island, you have a cluster of earth science. So these journals are all classified as earth science. And if you look at it, they are like anthropology and archaeology, which kind of makes sense because they use carbon dating and you basically need to dig up the earth. So it's classified as earth science, but they are actually closer to social science. And they appear as a kind of island that connect these two very distant fields together. So there are a lot of examples where it discover like highly interdisciplinary field across science. And we did a lot of validation, and it works so well. It works so well for like predicting like for instance how like human experts like judge their relevance to certain field and so on. And but the exciting thing is like you can do like crazy measurement that it's hard to think about, even hard to imagine in like traditional sense. Like you may know this SKCD comic. I sneak this comic into my reference in the paper. I'm very happy that I could cite SKCD. Yeah, so you can think about this because now we are working on a vector space. You put like social science and humanities on one end, mathematics and physics on the other end, project every journals and conferences on that axis, and you get the spectrum. And if you look at it, it basically matches what the XKCD comic shows. You go from like social science to like psychology, brain science, and so on, up until to mathematics and physics. But another interesting thing is if you choose different poles, it completely shuffles. And if you look at social to bio, then computer science appear much closer to social science than biological science. Although the computer science was much closer to mathematics and physics in this math to social axis. I think that indicate like this kind of space, the complexity of the space. Yes.
Excuse me, please correct me if I'm wrong. The vector representation is only the number of citations, the direction that each journal or conference cites each other. Or
It's at the paper level citation graph. And we kind of reduce it to journal level. Yeah.
Thank you.
And also we can do the king and queen level analogy, which is you pick two poles and find the periodical and you add and subtract vectors. So for instance, you can start from KDD or ICWSM. You can add social science and remove machine learning. And then you get like social forces, like social science journal. And if you add machine learning and subtract social science, you get things like ICDM, EMNLP, HTML, lyrics, and so on. And you can do same thing for pretty much every areas of science. And like, for instance, climate become like weather forecast if you keep adding social science. But if you keep adding like physics, it becomes like climate dynamics. So yeah, you can travel the space of embedding by just adding and subtracting factors. And we can, of course, evaluate that quantitatively, and it shows a really good result. Yeah, so this is one example that the visualization we are creating to explore the space of knowledge. And so basically vector space embedding of individual papers rather than journals now. And that kind of captures what's the kind of space we are thinking about. And you can see giant hole at the center. And you can see that hole in whatever representation of the scientific field. So you have like mathematics and chemistry, biology, medicine, social science, and then what is it? Yeah, it goes like this circle, and you can see that hole in the embedding space. And we can look at like does new science come about around the edge, the frontier of the current knowledge, or does it fill the gap? So you can, again, I think it's the power of this thinking about the space and thinking using our intuition about the space. We can ask like creative questions. Yes.
So, what accounts for the hole? Is it the distortion due to projecting it on 3D space, or is it something more?
I think it's real. Yeah, I think it's real because so many other representation and maps of science, they all shows gaping hole in the middle. But we actually looked at like few papers that appear in some of the holes, and one of them was like the psychology of force, kind of animal psychology, which kind of makes sense because we care about like human psychology, but not really animal psychology. But I think it's an interesting question, like what can fill that hole. Yeah. And other kind of unreasonableness, yes.
Just a quick question. Do you have some preliminary results to the question you asked? Does new research mostly come from the whole or come from the edges of peripheral?
It seems like it's more appearing in the like at the edge, but to be confirmed. Yeah, and yes.
How do you build 3D?
Huh?
How do you build the 3D
Yeah, well,
dimensional space
so one
from the embedding?
yeah, that's a UMAP projection.
So you map an embedding from which dimension? So 3 dimension.
I think it's 128 to 3. Yeah.
It's like how much this representation is like real in the sense that like how much do you lose information from this projection because
Yeah.
it's a nice shape like, if it's like human knowledge.
Yeah, that's a great question. So this visualization kind of allow us to draw edges. In the embedding space, we look at k nearest neighbors and draw edges, and then we project down and we can show those edges here. So I think there is some edges going across the hole. That's for sure. But it seems like even given what people has been showing regarding how science are organized, this seems very close to what kind of general knowledge is, like with one hole and surrounding kind of forest.
With pretty good representation.
That's my guess. But again, whatever we do quantitatively, we do in the original space. Yeah, because you lose information. Another interesting thing is once you get this paper representation, we can put authors as a kind of average vector of all the references they use, all the knowledge they draw, right? And then we can use that representation of the authors to predict who will collaborate in the future. And if you do this prediction, the embedding works best. It works much best than like other link prediction algorithms. Yeah, so why? Exhibit 2. Random walk is biased. If you do random walk on the graph, you tend to go to the hubs because hubs has more edges. You tend to sample hubs preferentially, and that's called French paradox. In other words, if you have a graph like this, and if you do a lot of random walks, you spend a lot of time at the core and much less time at the periphery, although core only has few real nodes. So the thing is, the implication is that if your embedding method try to predict what comes next in the trajectory, it should use the degree as a really important information because that's one of the biggest signal for the random walk. And actually, some methods produce this type of embedding. If you run graph embedding on the graph, like with a lot of hops, it picks up degree as the most important, most salient information. And it arranges everything based on the degree. So that's what you would expect. And some methods actually do that. But if you run like vanilla node to back, it doesn't do that. It works fine. It finds like much better representation. Exhibit 3, which is about mobility. So yeah, this work was done with the Kodamari, Jusanyon, and Kodamari Kodaku. So we used the scientific mobility data based on the affiliation of the scientists. So when you publish many papers, you can see your affiliations. Like we can construct the trajectory of the scientists based on their papers. Once you have trajectories or sentences, we can feed that into word to back, and we get the representation of the places. So here, not the scientists, but the places. Places are the words, and the sequence of places are the sentences. And when we think about mobility, there is a famous law called gravity law of mobility, which is inspired by Newton's gravity law. And what it says is really just you're less likely to move somewhere farther away than somewhere close. You can write this way, which is the flux between two locations is proportional to the population of these two locations. That's a good model, right? And then there's a decaying function, exponential or power law decaying function. And that's all it is. And it's the most basic fundamental framework that describes how humans move in the space. So we tested this with our embedding space. And it turns out that the distance in the embedding space follow this gravity law really well. If you look at the actual physical distance in the actual space, it doesn't so well, but the embedding space follows really well. And across multiple data sets. And we even tried to get the embedding space, like obtain the embedding space by optimizing for gravity law. Okay, we want to put these two nodes so that their distance satisfy the gravity law. And word to back works even better than that direct optimization. So it's crazy, right? How does it work better than optimization of your objective function? So there must be something aligned to that unreasonable effectiveness. Or there's something called detectability limit of community structure. If you have a network with communities, let's say just two communities with the same size, and then you can kind of make the problem harder by having more edges across these two communities rather than like having within each community. And if you keep mixing more edges, and the problem becomes harder and harder to find these two structures. And at some point it fails, right? And that's the algorithmic limit given a method. But the interesting thing is that algorithmic limit, in addition to this algorithmic limit, there is an information theoretical limit as well. So after that limit, although community structure exists, no method can find it because the fluctuation is great enough to mask whatever structure we have. And it kind of boiled down to this the spectra of the graph. So from random matrix theory, we know that if you have a two community structure, the spectra of the graph looks like this. You have a largest eigenvalue that correspond to the structure, and then all the other eigenvalue kind of distributed across this semicircle. And the thing is, like this when semicircle touches the largest eigenvalue, and you cannot distinguish these two, and community become completely obscure, although largest eigenvalue is not zero. Okay, so it's like a fundamental limit of the community detection problem. So there is a detectability limit where community structure exists. If you already know the community, if you measure some quantities, you can see that it's actually formed the community, but it's impossible to find it. So we tested many methods, including node to back. And it turns out graph embedding works really well. Yeah, so that dashed line is a fundamental detectability limit. No method can do better. No method can define community structure. And there are a bunch of methods, but if you run node to back on a graph, you have an embedding space. You do k-means clustering. In this case, we cheated a little bit because by telling k-means clustering, like how many clusters we have and where the center is, but to measure what's the inherent information in the embedding space. But still, it works really well. And even if we use like birch clustering without specifying the number of clusters and so on, it tends to work very well. So why does it work that well? It's not crazy because it's just the simplest method, embedding method you can think of, and no one is using it anymore because now we have all this graph neural. So I want to now talk about kind of partial answers to all these questions. So the first piece of the puzzle, the negative sampling that is used in word-to-back model. So one thing I didn't mention when I explained the word-to-back model was that to estimate this conditional probability and the vectors, we use negative sampling. And the problem is this conditional probability, the softmax, is nasty because whenever you change a vector, you have to recalculate the normalization term. That's a lot of computation. So the authors came up with something called negative sampling. So instead of calculating this with all the vectors, can we just replace that into contrastive learning method? Can we distinguish real and fake? Okay. And that can be written like this. And it looks a little bit complicated, but it's just a logistic regression. So basically, you are doing logistic regression based on true answer, the dot product with the true answer, and dot product with a bunch of random answers, fake answers. And if you can distinguish that, the more you can distinguish, the better you can distinguish, you have a better vectors. But one interesting thing is like negative sampling is a simplified version of noise contrastive estimation method. And noise contrastive estimation method is an unbiased estimator, but negative sampling is a biased estimator because it simplifies and removes one of the terms. So they look like this, and then Salamuri asked, what does negative sampling actually fit? Given the fact that NCE is an unbiased estimator. And we can do some computation, and then we can see that the negative sampling is actually not fitting the objective function of the word-to-back. What it does fit is a slightly modified version with a negative sample distribution in front of this Optimax function. So we have this extra term here. And that may look very different, but it has a really interesting property, which is basically we can consider this objective function into two parts. One is the first part is a baseline probability, what's expected, just based on random sampling, and then the remaining information. Okay, so the data we have, the sentences can be biased, and the bias comes from the biased baseline and unbiased radical. In other words, what you can do is why the word to back and not to back works better, so good, is that it has implicit bias that negates the biases from random walks and other processes. Yes. Question? Okay.
Why do we say random box is biased? Because like random box are probabilistic, right?
Yeah.
So there's always you can always make it equal probability to kind of choose any one.
Yeah.
And then
So, but if you do that, you tend to be biased toward hops because hops have more edges that can be sampled. So when you do random walk, you always bias toward high degree node. It's a proportional to the degree of the.
yeah, like if we don't do that, like use the equal probability.
Yeah, potentially we can change the random walk dynamics by considering kind of b-biased random walks. So that can be another approach to very similar thing. But I want to say is that word to back or not to back has a kind of inherent b-biasing mechanism that compensate for that bias. So you don't even need to change the word random walk process. So word to back model choice of narrative sampling was just for convenience because they are not interested in whether the model is biased or unbiased. They were interested in getting useful representation. And somehow, as a happy accident, it introduced this de-biasing mechanism into the model. And that kind of negates all kinds of like bad biases that comes into the model from the data based on the frequency. Now, two implications. The first one is a gravity law, which I mentioned random walks and the bias model, right? But if you apply that to gravity law calculation, you calculate the flux between two places and express that as this probability. And then if you do the calculation, it ends up becoming the gravity law. So in other words, word to back or not to back's objective function is same as gravity law. So it implicitly optimized for gravity law. So it's a kind of surprise for us that it's kind of sneaky in a way that it's secretly optimized for gravity law. Yes.
When you say like gravity law, are you like, is there any way to like find the equivalent with that formula? Like in the sense that we have that there's a constant and then there are like two properties of an object like mass, right? And then in this case, like is that exponential that we have there actually considering some properties of the nodes, and then pi and pj could be the distances.
Pi and pj are kind of mass of the two places, and then the distance term is exponential.
Okay.
Yeah, the product. Yeah, that's the difference. So because of this implicit bias that is not well known at all, basically the equivalent. So it makes sense that we get like really good embedding of locations when we put trajectory data into word to back. So the space we obtain by running word to back model on the trajectory is kind of optimized to satisfy the gravity law. So in other words, we are doing basically metric discovery, like what's the effective distance between two places based on how many people move between those places. So basically, it's doing that implicitly. And the implication is that whenever we have this trajectory data fed into word-to-vec model, get the embedding, and that can be literally interpreted using the framework of gravity law. We can calculate gravity potential of each location and so on and so forth. So basically, I said I'm recovering physicist. I end up doing physics secretly.
Can we like say like gravity potential would be like the degree,
Not there?
like like the degrees of the
Yeah, so degree,
gravity?
so degree basically tell you the baseline probability of reaching there, right? That's baseline probability. P(I), P0, there's no baseline.
So I mean like the other concepts like we have the centrality.
Yeah.
For example.
I think it may be interesting to explore the relationship, but yeah, I think degree is the most prominent. Yeah. And then we have a so-called residual embedding, which we published in Europe. So I said the objective function can be broken down into baseline and then residual. And this baseline basically let us remove this baseline frequency so that we can get unbiased residual. But the question is, can we remove any bias by plugging in that bias into that baseline probability term? And that's the idea of our method called residual to back. So we create explicit null model of transition between places, and we plug that into this place. And then what we get as an embedding is a residual of all that biases. So any bias that you can express as a null model in terms of transition probability, then we can remove that bias from embedding. Yeah, so it works like this, but the point is any kind of expressible bias in the graph structure can be removed. So one example is the citation graph. So each node is a journal year pair, and then citation edges are this journal year cite how many of these journal year. Okay, and it has a lot of biases, tricky biases to remove. For instance, there's a temporal recency bias. You tend to cite more recent ones. And then if you are old in terms of like journal year, you may have a more time to accumulate more citation. So you may have a larger degree. And there's also like field bias. Like there's a lot of structure in it, right? It's hard to address those biases. But what we can do is that we can construct a random graph model that targets specific bias. For instance, we can target temporal bias by shuffling the edges within the same year. And then we can get the embedding that is free of those temporal biases. Like, in these cases, you can see the color gradient going from like center to outside. That happened because this method picks up the time as a really important information to predict what comes next in the trajectory. But on here, it's more equally distributed because now we are ignoring the time information, and embedding is free of all the temporal information that is captured in our null model. And by in doing so, we can do all kinds of prediction tests much better. And other kind of lesson we learned is that this like unreasonable effectiveness, whatever I call it, may be coming from like the stochastic gradient descent and its power. Okay, its stochastic power, I'll say. So this is a kind of famous theoretical result from physics community that kind of describe where this information theoretical community detection limit happens. And this is the kind of the result, okay? But we can do similar calculation with the graph embedding, starting from the fact that graph embedding can be thought of as a matrix factorization. And then we can use like random matrix theory to think about like when that information theoretical limit may happen. So it's several pages of calculation, but at the end of the day, we get the same formula. Which means that the detectability limit of node to back, the algorithmic limit, is more or less same as the information theoretical limit. So actually there is a kind of fundamental mathematical nature of node to back that link node to back method to matrix factorization and then to the combination detection theory. And that's why it works so well for community detection. But the thing is, node to back works even better than more traditional network science-based optimal method. This method is supposed to be optimal up to the information theoretical limit, but node to back based community detection method works better. So that's puzzling. So we broke down like all the factors that may contribute to the difference. It can be due to the objective, linear versus nonlinear, and optimization algorithm like stochastic gradient descent versus like spectral decomposition and so on. So we created different models that fill all the quadrants, and then we run all the models. And it turns out that the objective function matters. The node-to-back objective function is non-linear, while the modularity more traditional method is a linear. It matters, but also stochastic gradient descent seems to be really good. So have you heard about this property of self-regularization of stochastic gradient descent? So it happens because, yes, so this is an easy problem. It's a dense network or whatever problem you solve. Okay, you have a lot of data, and your kind of loss landscape is very smooth. So global minima you want to find and be very or identical or very similar to what you can find by just optimizing toward the bottom using gradient descent. But the problem gets more difficult and sparse. The loss landscape may look like this, the more wiggly. And the global minima may not actually correspond to the theoretical best answer. So if you do really good optimization, you'll find the answer that's actually global minima, but it's different from the actual answer. But what happened in the stochastic gradient descent is that it finds like so many different answers essentially on the way and as an ensemble. So it kind of self-average many different answers. And in doing so, it may find closer answer to the true answer, even though data as a whole may not support it, because we are slicing the data into many small pieces and run it on those small pieces. Collectively, they may point us to the right answer. So that's our speculation. Yeah. Okay, so here's a summary. So I think the simple embedding methods are super powerful because, especially now, because we understand them much better, why they work and how they work. And sometimes you may not want to use a more complicated method because these methods are very theoretically can be grounded more firmly to the theories. And one important aspect of this method is this negative frequency bias that introduced by negative sampling, but it turns out to be a really good bias to be introduced to the model. And because of that, it matches gravity law, and we can remove bias, all kind of biases. And node to back is surprisingly have these nice properties of regarding community detection problem. Okay, so I'd like to thank my colleagues and teams and our funding agencies. And any questions? Thank you.
Just on the computational power required.
Yeah.
Like, you say like word and graph embedding are more efficient on the result, like because it's closer to the theoretical limit.
Mhm.
But like also on the computational power required, it demands less, right, than traditional method.
Yeah, it's another important point.
So it's like two burns. I mean, it's
Yeah.
doubly.
Yeah, it's even better.
Yeah.
Yeah. So node to back is a good point. Node to back or these methods that just require you to feed trajectories. And that can be really efficiently done without spending a lot of memory, for instance. You don't need to even store the whole network. So it's very efficient. And the stochastic nature of it also makes it, again, efficient. There was a really good paper from NLP community, why word-to-back works so well compared to more traditional methods. And like we can learn from it to do traditional methods better, improve traditional methods. And it's all about this efficiency and robustness coming from not constructing the metrics and just implicitly factorize the metrics directly. And the nature of stochastic gradient descent that's like self-regularizing and doesn't overfit.
So like, just to follow up on this computational restriction, like when you made the link with gravity law, which is like a physical or societal law, like could like those kind of methods could be adapted to optimize real computation of gravitational real optimization of gravity law. Do you know what I mean? Like, using some kind of representation that can use node to back to compute like physical optimization with less power.
Yeah, that's
It's so close to.
that's a great question. For instance, in the gravity law case, like direct optimization using like MDS require a lot of computation.
Yes.
But word-to-back works even better than direct optimization. Yeah, so that's I think one example. But I think there can be even more example where this type of method, if you figure out what the objective function does, then for the problem that optimize that objective function, we can use word-to-back or other methods rather than directly optimizing that function.
So what your research found can be like an entry point to a lot of different like new methods.
Yeah, potentially. Yeah, potentially. But I think understanding what objective function really do, I think that's the challenge, and finding the problem that matches exactly. Yeah. I mean, neural networks are amazing. It finds this type of answers really well.
Trying to think of if residual to back method could be used as a way of theorizing, coming up with explanations.
Yeah.
You have the baseline,
Yeah.
bias, and you have a set of known biases. that can all be accounted for.
Mhm.
Then you're left with something and you observe these distances in the space.
Mhm.
Could you give an example of how that could be used in explaining the?
Yes, yeah, I think that's a pretty good question. Yeah, that's what I like most about the method, which is it allow us to explicitly model the bias and construct the bias model. And then we can talk about like what's left, what's removed, right? One kind of maybe not along exactly the same line of what you asked, but one thing we are doing is kind of link prediction and recommendation case. So like if you think about like recommending professional link on LinkedIn, for instance, or similar services. Given the current power structure and like strong homophily in social network, if the recommendation engine use homophily as a really strong signal, then it may not recommend links between like more a community with power and the more marginalized community. So it may be good to force the model not to use that type of information. So we can construct, for instance, a model of like ethnicity, for instance, or gender, or both. And then we construct the model so that we can remove the bias, remove that exact bias, and then see what's left and how well can we do regarding link prediction and how we mix different populations and so on. Yeah, I think it would be really cool to think about like, what's left.
So link prediction would be one,
Yeah.
one way to think about it. Maybe another way would be to look at what the existing links, the empirically observed links, and see if you can explain the links that are not likely.
Right, yeah.
So,
yeah.
for example, you might have two people who are very different.
Uh-huh.
They don't share any interests or attributes. They don't share any common neighbors, and yet they have a link.
Yeah, I can see what you're thinking
Yeah.
regarding your paper. Yeah, I think that would be really interesting study. Yeah, thinking about like evaluating what are the most unlikely social connections. Are they much stronger or not? Yeah, that would be very interesting. Other questions?
And actually, like, so why did you choose residuals in this process? Because to develop an unbiased estimator, there are many other ways to do it, right? Like not necessary to look at only residuals, for example. I'm just coming from the angle of like, let's say like in the regression model,
Yeah.
you have a biased estimator, you actually correct it in the coefficients, for example, not the residuals.
Yeah, so we were very opportunistic in a sense that we discovered this mechanism to remove bias so that we get the embedding that is free from that bias, right? So we discovered it. So it was like really simple, like can we put arbitrary bias model to remove such bias from the embedding? And I think it's not super trivial to remove bias from embedding. So you can potentially like change the data, input data, like gender, for instance. You remove all the gender specific words, for instance. But I think they tend to degrade the quality of embedding quite a lot because you are removing a lot of information. Or like it's not guaranteed what you are removing exactly, depending on how you process the data. So there are a lot of issues with the kind of more non-explicit biased model. But here, I think, again, what I like most about it is that it allows us to write down in terms of conditional probability, what is your bias model? And we can study that bias model. And then we can kind of ensure that that part of the bias is removed.
Yeah, so I think here we are looking at bias from two different perspectives.
Yeah.
Right, one is the statistical bias.
Mhm.
And I think your claim is that you're trying to fix that using residuals by
Mhm.
correcting for it.
Yeah.
And then also that indirectly affects the social bias that you see.
But
that-
in a way, we have a way to describe a social bias or whatever bias as a statistical bias. And then we have a way to plug that into the model to remove it. Yeah. So basically bridging whatever you thinking about social bias, we force you to specify that bias in terms of statistical bias. And I think it's good thing to do because we want to know exactly what we are removing. A lot of embedding debiasing models tend to use like, okay, here is a bias we are seeing, and we kind of force them into certain based on some linear assumption. But it's not guaranteed that we can remove that bias without introducing other biases. So I think it's I'll say potentially much better way to encode that into mathematical concrete
Yeah.
model. Any other questions?
Like, I think the other thing that you're also trying to say is this method can be superior to graph neural networks or like equal accurately.
It depends. I think this type of simpler method works better when you don't have a lot of data, first of all. And then second is interpretability. When we use this model, we understand the objective function fairly well. We know that it's, for instance, connected to gravity law. We know that it has this implicit bias, and the negative sampling remove at least the frequency bias. So we know those things. So if your problem requires more grounding, I may use this type of simpler method that is more transparent, and we know more about it. But if it's like a case where what matters most is like accuracy,
No, I mean,
then yeah, graph neural network may be a better choice, depending on the problems. Right? Sorry.
It's a fair question. I'm very new on graph embeddings. You mentioned choice of dimension a bunch of times, like when you show the metrics
Right.
vectorization, like the question
Yeah.
mark. So again, I don't know that much. Is the choice of the appropriate dimension directly in the model? Is it something we choose a priori and then we evaluate? So how does that? Like,
Yeah, it's a hyperparameter that we need to choose. We have another paper on dimension of the graph embedding. What we know about choosing choice of this is that if it's too low, too small, it hurts all kinds of performance. But too low is quite low, like it's like 4, 8. Like sometimes even like 8 dimension is enough to capture most of the information in the graph. And there was another paper, more recent paper, that argue most graphs we are dealing with, they tend to have a really low inherent dimensionality. So there were some of their papers. Another kind of cool thing about graph embedding and all this neural network method is that increasing number of dimensions doesn't hurt much. It's probably due to the self-regularization of the stochastic resolution. But even if you double the dimensions, there is almost no trade-off regarding like bias variance.
Overfitting, like having too high of a dimension.
Minimal overfitting, yeah. So if you're not sure, you can use big enough. Yeah. And given that most networks have a very low dimensions, like if you choose like 100-ish, it usually works fine. And most of the studies we've done, actually all of the studies we've done, we've tested multiple dimensions.
So, what's next? in this
Uh, yeah, good question. Yeah, the project I mentioned about social bias, removing social bias from link prediction. That's one thing going on. We are kind of digging into how scientists move and find new topics, collaborate, work together. So this type of like social dynamics in science. We are trying to understand other things. Yeah, so generally a lot of projects focus on science of science applications. But yeah, there can be many studies regarding social media or other systems.
You do the analysis that uses citation graphs as the input, as opposed to similarities in words. What different conclusions do you reach about the similarities of fields?
Yeah, that's really interesting question. So we have done both. In some studies, we use like a title abstract to obtain the embeddings. In some studies, not back based on citation graph. Sometimes we compare them with each other. In terms of like downstream performance, like predicting citations, predicting collaboration, it seems like they are similar, where but like graph embedding seem to do a little bit better in terms of just pure performance. But really interesting question is like how different they are and what kind of difference they capture in science, right? This field may be really close together in graph embedding, or maybe a little bit farther away in text embedding. And that may signify how they are done. Like citation is about like citations, references, and the language is about like what kind of language they use. So if they are closer but different, closer in graph embedding but farther away in language, that means they use different language, but still they are intimately connected in terms of in kind of knowledge they draw. It can be vice versa. They may studying the same thing in terms of language, but they may not be connected in terms of citation. And it may happen quite often because of the disciplinary silos. I may studying social media from like informatics department. Someone in like political science maybe studying the social media, like it's the same thing, but we may not know each other work and we may not cite each other. So that's one of the things we are thinking about and working on. We are finalizing a paper that compare text embedding and graph embedding, but it was just purely quantitative. But I think really interesting question is like what makes them differ.
That's it. It's about time we can take the other questions offline.
Okay.
Thank you very much.